welcome to the new participants. We continue our mini program with this week of lecture series. So our first speaker again is Bena Tshishiku, who will talk about exotic negatively curved manifolds. And there will be some announcements during the days and during the week. So they might, there are some changes in the program, but all will be in place. So please keep following. And whenever you have any questions, please feel free to ask me or people in the office or anybody around. Thank you.
Okay, so thanks for the opportunity to speak. So the goal of these minute courses, the main focus will be to explain the following theorem, which is, so the statement I'm going to write is due to Farrell and Jones and also Antoneda. For every n at least 6 and positive epsilon, there exists n, which is a closed Riemannian manifold with pinched curvature. So sectional curvatures K is negative and pinched. That is homeomorphic but not diffeomorphic to a hyperbolic manifold. Okay, so let me start by giving some context and motivation. And hopefully that will help us warm up to the statement, understanding what this is saying. So the first is about exotic smoothing. So this theorem is providing exotic smooth structures on hyperbolic manifolds. So the first comment is that in dimension less than or equal to 3, homeomorphic smooth manifolds are diffeomorphic. But this is generally false in dimension at least 4. So for example that will be relevant in a bit is that so S7 has 15 smooth structures. Up to diffeomorphism. Right, and so the theorem is saying that hyperbolic manifolds, so high-dimensional hyperbolic manifolds, can have exotic smoothings. Can have multiple smooth structures. in particular. That's part of the statement. Okay. But it says more than that. So it's also saying that these manifolds can emit negatively curved metrics. Right, so these examples belong on a very short list of known constructions. Of closed negatively curved manifolds. So let me just give you the list. So there are the locally symmetric examples. Like quotients of Hn, complex hyperbolic space, and so on. There are branched covers. There's various branch covering constructions. So you can take one of these examples, for example, and take branch cover over a totally geodesic submanifold. So we saw this last week. The first construction of this type is due to Gromov and Thurston. There's other versions of this. This was branch covers of hyperbolic manifolds. Maybe I'll mention one recent result in this direction due to Stover and Toledo constructs branch covers of complex hyperbolic manifolds in every dimension which emit negatively curved metrics. There are hyperbolizations. So this due to Charney-Davis and Antoneda. We also saw this last week in John's talk. And then there are exotic smoothings. Okay, so someone can correct me if they know of some other example, but as far as I know, these are like a complete list of the known constructions. And maybe also mention that somehow these are all constructed using like arithmetic hyperbolic manifolds. So, well, okay. Right, so yeah, we somehow saw all of these last week. And so, well, this week you'll learn the last one. Okay, so then the next comment is about rigidity. And please feel free to stop me at any point if you have questions. Okay, so yeah, so in studying manifolds, you can consider them up, in different categories. So, you could consider them up to diffeomorphism, or maybe homeomorphism, or the weakest is homotopy equivalence. And of course, if you're diffeomorphic, then you're homeomorphic. And if you're homeomorphic, then you're homotopy equivalent. Maybe the strongest thing you could put here is, if in the Riemannian categories, it could be isometric even. And one way to phrase, well, rigidity, or just one question you could ask is, can you ever sort of reverse these arrows? Like homotopy equivalent things are homeomorphic. In some, generally you'll need some additional hypotheses. What I'd like to do now is write 3 statements like that. One of them is going to be true, one will be false, and one is a conjecture. And I'd like you to figure out which is which. Okay, so the first is that homotopy equivalent aspherical manifolds are homeomorphic. This means that this is closed. And aspherical means the universal cover is contractible. So all the higher homotopy groups are 0, and there's just pi 1. Okay, the second statement is that homotopy equivalent hyperbolic manifolds are isometric. And then the last one is homotopy equivalent negatively curved manifolds are diffeomorphic. Yeah, sorry, I should say closed, everywhere, closed. Okay, so I think you won't have too much trouble, but maybe let me just give you 30 seconds to think about it. Feel free to discuss with your neighbor, and I want to hear what you think. One is true, one is false, and one's a conjecture. Okay, let's see. What do people have any thoughts, ideas, or even questions about the statements? Oh, yeah, okay, sorry. Sorry. Maybe here, dimension, okay. I think other than that. Yeah, thank you for that. Okay, maybe from the students, can I hear some suggestion? Yes?
So that theorem seems to say that the third one is false.
Okay, yeah, so this is false. Okay, good, you're paying attention. So this is false. So this was a conjecture of wait, let me make sure I don't mess this up, of Lawson and Yao. But the theorem gives counterexamples to this statement. Okay, how about the other statements? Yeah, so this is Mostow rigidity. So this is, yeah, so that's true. This is Mostow. Yeah, and you need to mention at least 3.
I think this is true also for finite volume.
Yeah, right. So, right, we could strengthen this slightly. But okay, right. And then this statement here is known as the Borel conjecture. And it's generally open. It's known in many cases. For example, it's known for hyperbolic manifolds by work of Farrell and Jones, but in general it's open. It says that a spherical manifold should just be determined by its fundamental group. Homotopy equivalent is if and only if you have the same fundamental group. And that's the only interesting homotopy group since you're aspherical. So somehow that should determine everything about the topology. That's at least the conjecture. You can think of it as a version of the Poincare conjecture for aspherical manifolds. OK, good. So now I have one more remark. Yeah?
Hyperbolic, you mean negative curve for the first, and for Farrell-Jones solution?
Oh, yeah. So, well, yeah, so first they proved it for hyperbolic things, but then for negatively curved. Now it's known pretty much for all the examples we know where there's some negative curvature, which could be like the fundamental group is a Gromov hyperbolic. Yeah. No. This so good. So here in this statement, you start with So let me say the precise statement. So you have one manifold which is hyperbolic, and then you have some mystery topological manifold. You don't even know at the beginning that it has a smooth structure, and all you know is that it has the same fundamental group. Okay, so these things a priori could exist, and the statement is that they don't. Is it okay? Yeah.
But if they're negatively curved, it's known.
If they're negative, I don't really want to go into the full of what we know, but yeah, for negatively curved manifolds, if you have another manifold which is homotopy equivalent to it, then in fact it's homeomorphic. And that's work of Farrell and Jones. Okay, let me give one more bit of context or motivation, which is connection to harmonic maps. Okay, so so there's a notion of what it means for a map to be harmonic between Riemannian manifolds, something like your critical point for some energy functional. I don't want to say what that means, but okay, so I just want to explain how the theorem is connected at all to harmonic maps. So let me first tell you a fact, which is if you have maybe these should be closed. If you have any map from any closed Riemannian manifold into a closed Riemannian manifold with negative curvature, this is homotopic to a unique harmonic map. Okay, so in any homotopy class, there's like a best representative, which is the harmonic map. And it should be something beautiful. So for example, an instance of this is if you take here a hyperbolic manifold, and here the circle is saying like any free homotopy class has a unique geodesic representative, which is maybe you know for other reasons. Okay, so a possible strategy to prove the Lawson-Yau conjecture, and I think, or maybe Borel for hyperbolic manifolds, is, well, to prove either of these statements, you start with a hyperbolic manifold, like I was just saying, and you start with some mystery thing, which is homotopy equivalent. Okay, and then the theory of harmonic maps gives you for free, or with work, that you get you can replace this homotopy equivalence by a harmonic map. So you start with some floppy thing that you don't have any control over, and then you get a harmonic map. And then, well, what you'd like to do is to show, you would win if you could show that every harmonic homotopy equivalence is a homeo or a diffeo. Okay, so you just prove some general fact about harmonic maps. They're supposed to be like the nicest representatives, so maybe this is reasonable. Well, but so on the other hand, so the theorem implies, well, yeah, so if you could do diffeo, then that would prove the Lawson-Yau conjecture. You start with a homotopy equivalence, you get a harmonic representative, which should be a diffeo. So the theorem implies that harmonic homotopy equivalences need not be diffeos. And later, Farrell and Jones and maybe Antoneda as well showed that you could replace this by homeos. Yeah. Does what? Injective. Oh, yeah, so that's what they show. They show that it doesn't have to be injective. Yeah, that's what they show fails, yeah. Mm-hmm. Yeah, so there's, this is kind of the beginning of a whole story of trying to understand. There's various geometric constructions. Like another example is, which is related to Mostow rigidity, is there's the Besson-Courtot-Gallot map in the proof of Mostow, and you can also show that those maps don't have to be diffeos or homeos in between negatively curved manifolds. That's a side comment. Okay. Right. So let me pause and see if there's any questions. Yes?
Manifolds and Hyperbolic is
Say again?
what kind of maps do you have?
Where? Here? Or in the fact? So this is just a continuous map. And the key is that the codomain is negatively curved. And then the domain can be anything, yeah. Okay. Other questions, comments?
What can we say about dimension 4 and 5?
Yeah, so that is unknown, like if there's a version of this in dimension 4 or 5. But the closest thing, there's some recent work that's closely related. Let me just mention that since you asked. So there's work that appeared just last month. Davis, Hayden, Huang, Ruberman, Snook-Chian. Let me not write the statement, but let me just say it in words. So they show in dimension 4, you can have aspherical manifolds with multiple smoothings. And these have a hyperbolic fundamental group. Okay, they're not hyperbolic manifolds, but they're aspherical with Gromov hyperbolic fundamental group. But yeah, as for whether hyperbolic manifolds can emit exotic smoothings, that I believe is open. Anything else? Okay, so right, so the goal of the lectures is to explain the ideas and ingredients related to the proof. So this is going to involve, like, there will be some uses of rigidity. In some sense, this will be something of an invitation to high-dimensional manifold topology, and there'll also be some Riemannian geometry ingredients. So let me start by just telling you a strategy for proving the theorem. And the strategy is quite easy. So you start with M, a closed hyperbolic and then you take sigma, a exotic n-sphere, and then you take n to be M connects some sigma. Okay. And then what you need to do is there's three things to show that N and M are homeomorphic, N and M are not diffeomorphic, and then that N has a negatively curved, pinched metric. Okay, so that all sounds nice and good, but in practice, it's not quite that easy. Yeah, so, okay, so actually well, okay, so let's see. Let me make some comments about this. Yeah, okay. So maybe the first comment is that these two manifolds are homeomorphic is easy. And we'll see that later, within this lecture. But the second remark, so this statement one, well, it's not generally true. That when you connect some with a exotic sphere, then you still have an exotic smooth structure. So let me just give you an explicit statement. So for example, if M is 9-dimensional and non-spin, then there exist homotopy 9 sphere such that M connects some sigma is diffeomorphic to M, and hyperbolic manifolds that are not spin are known to exist. So this statement follows by combining, well, work of Martelli, Riolo, Slavic from not too long ago, with older work of Munkries. So that will give you examples like this. So upshot, connect some with an exotic sphere is not always an exotic smooth structure. So we'll have to understand when that might be, when this might hold. And then, yeah, so let me just also say that this negatively curved metric will show using warped product metrics. Okay, so just to give you some hint for what warped product metrics on annuli. Okay, so ultimately it will boil down to that. And this will also require some assumption on M. Okay. Right, so let's see. Yes, question?
What if for a given n there are no specific spheres?
Ah, yeah, great. Oh, yeah, I think I was, yeah, thanks. I wanted to say that too. So this strategy only works in dimensions with exotic n spheres. And in particular, I'll just remark that, well, there don't exist exotic 6 spheres. Okay, and that's, according to the statement, the first dimension where we should see some examples. Okay, so, right, thanks for pointing that out. I'll come back to this once we see a bit more about the proof. Okay, so yeah, so this strategy will only prove part of the statement of the theorem when you have in that dimension an exotic sphere. But we'll discuss what to do in general as well. Okay, any other questions, concerns at this point? Okay, so in the rest of the lecture, I hope to be able to, so I want to say something about exotic n spheres, and then introduce this notion of a warp product metric. Okay, so I'm going to start with the exotic spheres. Oops. Okay, so first the definition. So A, homotopy, n sphere is a closed, smooth, manifold that's homotopy equivalent to Sn. This condition can be phrased just in terms of algebraic topology invariance. Characterization is that the fundamental group should be trivial, and the homology should be the same as the sphere. Okay, and maybe, so the word exotic, so let me just explain what that means now too. So exotic, well, maybe I said this already, but let me just say it again. this is homeomorphic but not diffeomorphic. Maybe it was implicit before. Okay. Right, so what I'd like to do now is give you some examples. This will be 4 constructions of exotic S7s. So my goal is just to give you the sense that these aren't such exotic. I mean, I think exotic almost is an unfortunate term because it makes you think these are like weird things that you would never find in nature. I'd like to try to convince you otherwise. And you might even think at some point in this next part that, oh, even I could have discovered exotic spheres. Okay, so the first construction is what are known as Brieskorn spheres. And these are, so this is for the algebraically minded. So okay, so I'm just going to write down a variety, a real variety. I wrote this down last week. Okay, so that's it. So so we're in C5. You have the vanishing locus of this thing. So this is 10 real dimensions. This will be some 8-dimensional thing. And then we intersect with the unit sphere, which should get us down to 7 dimensions. Okay, and well, it turns out that's a exotic 7 sphere. And right, so I'm not going to explain why. I'm just going to give you the construction. I'm not going to explain why these are. That would take too much time for what we have. But let me just remark that if there's a low-dimensional variant of this, which may be more familiar. So this is the, so this is now so we're in 6, this is a 3-manifold, and this is the Poincare homology sphere. One characterization of the Poincare homology sphere is is a branched cover of S3 along the trefoil knot, which is equal to to this locus. Okay, that's the first example. I won't say too much about any of these, but all right. The second example is for the more topologically minded. So this is the Milnor spheres. Yep. Oh, yeah, it's a 5-fold. Right. Up to rescaling, if you just forget the z coordinate, then you get a map to S3, and then each point will have 5. Yeah. Okay. Okay, next, the Milnor spheres. These were the first ones to be discovered. So these are bundles like this. Well, so for each pair of integers, you can construct a bundle like this. It's a 3-sphere bundle over S4, where the way to build such a thing is you view the 4-sphere is built out of 2 disks, 2 hemispheres, and the bundle over each of those is trivial. And so this gives you, any bundle like this will have a description as a union of 2 D4 times S3s glued along S3 times S3. So you just have to specify, so identify a gluing map so the picture is, so we have, and over each, so maybe this is my X, and I have a 3-sphere fiber over X and another 3-sphere fiber over the same X on the equator, and I need to say how to identify them, okay? So this will depend on these parameters I and j, and the formula is like this, where we view S3 as the unit quaternions. Okay, so here this is multiplication of unit quaternions. Okay? Okay, for each I and j, that gives you a bundle. And then I'm going to take sigma 2 to be E 2, comma 1. 1, comma 2, comma minus 1. Okay, so I and j are these indices here. Okay, that's the second construction. The third construction is known as plumbing. Could have been discovered by anyone who is a plumber. So let me start with, here I'm going to start with the E8 diagram. And then, so here's the construction. So for each vertex, so for each vertex, I'm going to take EI, which will be a space. There's going to be a copy of DS4. So this is the unit, or sorry, this is the unit disk bundle of the tangent bundle of S4. Okay, so I'm going to build, I have to build a manifold for you. Okay, so this is the beginning of it. I take this diagram. For each vertex, I take the unit disk bundle of S4. And now for edges, I'm just going to draw a picture. Right. So this picture is like the well, okay. Okay, so this is like EI and EJ connected by an edge. And so in the picture, this is the D4 direction of the bundle. And also here, these are D4s. And for example, like the unit disk bundle has a zero section, which would be a copy of S4. And those are, you see here. Okay, so in general, the construction is you fix a disk in S4 in the base of the bundle. Over that, you see, so that's a 4 disk. Over that, you see D4 times D4. In the other bundle, you see the same thing, D4 times D4, and then you identify them by factor swap map. Okay, so the fibers of the one go to like parallel copies of the base in the other. Okay, does it make sense? This is literally the picture for plumbing if I take S1 times R, like the trivial bundle, over S1, the rank 1 trivial bundle. This is the plumbing of that. Okay, and then, so what that gives you is a, so here, these are 8 manifolds with boundary. The result of that, so that gives you a manifold P, which is, this is an 8, this is a manifold with boundary. And then sigma 3 will be defined as the boundary of P. Okay. One more construction, and then I think we'll take a short break. So this last construction is for people who like representation varieties. And you'll see why in a second. Well, I'm going to call this like a Heegard splitting construction. So the basic construction is to build, so here psi is a map from S3 times S3. So a diffeo. Okay, this kind of looks like what I did here, but it's different. Well, so let me just say, for example, if psi is the identity, you get S7, which is viewed as like the boundary of D4 times D4. Okay, so, right. So for this construction, we need some interesting self-maps of S3, interesting gluing. And, right, so for this, let me give you the most highbrow way to write down S3 times S3. So S3 times S3, so first of all, S3 is SU2, the compact Lie group, SU2 times SU2. And a pair of matrices in SU2 is the same thing as a homomorphism of the free group of rank 2 into SU2. Okay, so that's the representation variety of the free group, SU2 representation variety. And, well, right, when you see this, then you get a little bit excited because this has an action of aught F2. And so then you get a lot of diffeomorphisms of S3 times S3 out of this. And so, for example, if you take A to be, so I'm going to write F2 as generated by X and Y. Or let me say A and B. And then A, this will be an, let me give you a pair of automorphisms. So first, A will be an automorphism of F2. This sends AB to A, comma, A, B, A inverse. And B will be similar, but with B conjugating. And then, so these are elements of aught F2. And then yeah, so the last homotopy sphere, sigma 4, will be M, A, B, A inverse, B inverse. Okay. Okay. Any questions about any of the constructions?
I think you messed up something
Yeah.
when you inside because I mean that's not a manifold bound. Do you mean like
I want this to be like a closed 7
oh, okay.
dimensional manifold. Yeah.
Also, then can you explain what is this
Oh.
S7 equals the boundary?
Yeah. So so what I meant to say by this is if you think of D8 as like D4 times D4, then the boundary of it is D4 times S3 union S3 times D4, where the gluing map is, I think, the identity, or yeah. Okay. Other questions?
So then are the Reese-Horn spheres crash covers of things inside S7?
That seems likely, given what I said about the Poincare homology sphere, yes. But as for what that thing is, I mean, I guess it would be something like if you delete this coordinate. Yeah. Right. Okay, so what I want to do after the break is I will tell you just a little bit about the general theory of homotopy spheres, give you a couple of structural results, which will be helpful going forward, and then hopefully say something about warp product metrics. Okay, so maybe we could take a 5-minute break and come back at 11:30. Okay, so I hope I made you a little less, if you were intimidated by homotopy n spheres, hopefully you're a little less so. Let me say a little bit more. So, which will be useful going forward. So all of this will be dimensions n at least 5, all of the. So just keep that in mind. And I'm going to start, so theta n will denote the set of homotopy n spheres oriented with an orientation. They're always orientable, up to orientation preserving diffeo. Okay, so at the beginning, this is a set. Well, the first thing you could see is that this is an abelian monoid under connected sum. If you have two homotopy n spheres, you take their connected sum, you get another homotopy n sphere. It's not clear, at least at the beginning, that you have inverses, but we'll see that in a second. So the main theorem I want to state here is identifies this theta n with a certain mapping class group. Okay, so this is orientation preserving diffeomorphisms of the n-1 sphere. And pi naught, this is taking path components or isotopy classes. And an isomorphism, the isomorphism is given by clutching. So it'll be a map in this direction from the mapping class group to theta n, which you just draw the picture. If you have phi here, then you can take two copies of dn and glue them along their boundary, which is a n-1 sphere by phi. And that only depends on the isotopy class of phi. And the theorem is that this is a bijection. Okay, let me just say briefly the ingredients of this. So this is, let me just emphasize again, in dimension at least 5. And yeah, so the ingredients are, so the H-cobordism theorem, which is a high-dimensional fact due to Smale, and pseudo-isotopy theory. So I'm not going to say more about this, but I think in the exercises there will be an opportunity to learn a little bit more. So there's a particular theorem due to surf that, yeah. But the main thing I want you to take away is that, yeah, so I gave you all these different constructions, but in fact there's a uniform way to build homotopy n spheres, which is this picture. And in particular, one corollary of this is that every homotopy n sphere is homeomorphic to Sn. And yeah, so just remember, we're always in high dimensions here. So let me explain why this how this follows. So let me give this thing a name. So sigma. So sigma, we can write it so as dn union dn glued over phi. And phi, so I want to argue that this is homeomorphic to Sn. And well, one way to do that, so phi extends to a homeomorphism of the n disk. Maybe I'll call that phi hat. And using that, you construct a homeomorphism, well, yeah, so, well, let me not spell out this part, but once you know that phi extends, then that sort of tells you you can do the identity on the first disk and then do the extension of phi on the second disk, and that will glue to a homeomorphism. And yeah, this is a little exercise. This will also be in the exercises if you want to think more about how to do this precisely. This fact that phi extends to a homeomorphism, this is called the Alexander trick. And well, you can write an explicit formula for phi hat, and maybe you've seen this. Okay, so you just do phi on concentric circles, and then you fix the origin. And then, well, yeah, so this is a perfectly good homeomorphism. Most likely you don't have smoothness at 0. So it's a homeomorphism, but probably not a diffeo. Okay. Right. A little bit more about this theta n. Crivera-Milner. So far, well, from this, you do get that theta n has a group structure, because this is a group, it's a mapping class group. Crivera-Milner studied more closely the structure of this group. And, well, they show theta n is a finite abelian group. And in particular, the inverse of some homotopy n-sphere is the homotopy n-sphere with the opposite orientation. Okay, that would be useful to remember. And they prove lots of results about the structure of these groups. I think I won't say too much. And they also give some low-dimensional computations, which maybe I'll just give a few. There's the first few. Yeah, so in general, there's a lot known about the structure of these groups, but not everything. Part of the group structure relates to the stable homotopy groups of spheres. So understanding this is no easier than understanding that. But at least there are structural results and some computations. Right. So a couple of comments. So it's unknown if there exist exotic S4s. I think Many four-manifold theorists are thinking about this these days. Another comment, some dimensions have no exotic spheres. So this comment came up before, like 5 and 6. There's a not too long ago result of Wang and Xu that says that there's no exotic 61-dimensional spheres. Turns out that's the last odd dimension where there are no exotic spheres. Okay, and then the last thing I want to say about this is, so theta 7, Milner and Crever show that it's isomorphic to Z mod 28Z. And so in particular, I gave you 4 exotic 7 spheres earlier that they have to be closely related. And in fact, sigma 1 is sigma 2 is sigma 3 is sigma 4. And it generates this group. Mm-hmm. What happened? Something is wrong. Something seems wrong. Yeah. So let me just say very briefly. So one thing Crever and Milner prove is there's a short exact sequence for theta n. Oh no, it's not a short exact sequence. There's an exact sequence like this. So this group is so it relates to Bernoulli numbers. So it's cyclic, first of all, of order related to Bernoulli numbers in dimensions n is 4k minus 1, and 11 is one of those. So there's some, so in dimensions 4k minus 1, these groups tend to be huge. So I also have in my notes dimension 15, there's 16,256. And then this part is the part that's related to stable homotopy groups of spheres. So co-kernel J homomorphism. And that's the more mysterious part of theta n. Okay. Other questions? This is all I'm going to say for now about homotopy spheres, exotic spheres. Yeah?
Is it easy to see that there are infinitely many dimensions where they do exist?
Where they do exist. So I guess in like all of these dimensions, 4k minus 1 will be non-zero. Okay. All right, so now I'm going to switch gears and introduce a bit about work product metrics, which will be crucial to understanding how to put negatively curved metrics on these manifolds. Okay, so for us, what this is a tool for constructing k less than 0 negatively curved metrics. Okay, let me start with a couple of examples, and then I'll give you a general definition of what a warp product metric is. Okay, so so this is a formula for the standard Euclidean metric on standard metric, Riemannian metric on the Euclidean plane. In polar coordinates, it looks like this. I'm going to use T. Polar coordinates T theta, where T is the radial coordinate. Yeah, this makes sense. It's like the circle of radius. Well, anyway. That's another, and this is going to be a warped product metric in a second, or it is already. So the second example is R2 with metric sigma is hyperbolic sine squared t d theta plus dt squared. Is a model for the hyperbolic plane. So this is a metric of constant curvature -1. We'll see why in a second. But OK, these will be basic examples of warp product metrics. So you can kind of see they have similar sort of structure. Now let me tell you the general definition. Oops. Okay, so M beta will be a Riemannian manifold. And so the setup, you have M, you have J, which is an interval in R. And F will be a function, a positive function on this interval. And then the warped product, which is written like this, M times J over F. It's defined as, so it's the Riemannian manifold, which is just the product, M times J, with Riemannian metric alpha, given by the formula f of t squared beta plus dt squared. Okay, so yeah, I'm just going to give you some examples to help understand what this means. So the first example is surfaces of revolution. Have a warped product metrics. Where here M is S1. And yeah, so this function F is telling you, so in a warped product, you just have many copies of your manifolds. which are varying in, you're scaling the metric as you vary t, the parameter in J, okay? Okay, right, so before more examples, let me give you an important formula that tells you the curvature of a warped product metric. So this is Bishop-O'Neill formula. Right, so this, okay, so as before, M, we have M, this warped product, where the metric I'm denoting it alpha. So the formula is for the sectional curvatures of alpha. Let me write it down and then explain what it means. Right, so here, we maybe have fixed some point p comma t in m times j, and x and y, x1 and x2 are tangent to m, and y is tangent to the r direction. Yeah, p-t. So in a picture, so we have one of these slices, the teeth slice, have a point P in M, and x1 and x2 are tangent like this, and this is x1, x2 maybe, and then y is pointing in the orthogonal direction. Could be up or down. X1 plus y and x2 are an orthonormal basis for the two plane they span. Okay, so yeah, if you want this formula to work, you need to choose orthonormal basis. Otherwise, it's a worse formula. Okay, so, right. So let me just give a couple of examples, a couple more examples, these warp product metrics. Yeah. Oh, yeah. Yeah. So beta was our original metric on M. It should be in the notation here. So M beta. And x1 and x2 are tangent to M, and this is the curvature in M of that plane. Thanks. Okay, just a few examples. So all right, so let's just compute the curvature of this warp product. Okay, so this I want this to be the unit sphere, round sphere. So constant curvature 1. Okay, so So K alpha is okay, so we have second derivative of sinh, which is sinh over sinh, which is -1. Times the norm of y, squared. I probably left out the squares are there. Okay, great. And then plus 1 minus cosh square t over sinh square t. And then this is, so minus norm of y squared. You look up the trig identities, and this is -1. And so x1 plus y is unit length because there's an orthonormal basis. And so this is -1. Okay, so this is a model for hyperbolic space. And this is the metric you get on hyperbolic space from pullback of, so you take Rn plus 1 to so you take the hyperbolic disk model of hyperbolic space. At the tangent space at the origin, you have the exponential map. And you pull back the metric, this is the formula you get. Okay. Okay, I'm out of time. Maybe I started a minute late. Let me just very quickly give 2 more examples. So if you take the torus, flat torus, and you take f with the warping function e to the minus t, you check that this is also hyperbolic metric. And this is the model of a cusp in hyperbolic geometry. So as you go out to infinity, it shrinks exponentially fast. Okay, and then, the last, so just to give you an example. So if you do r times r with warping function cosh, or then you get hyperbolic space again, different model. If you take hyperbolic space times r with warping function cosh, you get hyperbolic n plus 1 space. Okay, so you can, well, if you want to just get familiar with the curvature function, you can check these examples. Okay, so next time I'm going to start by using these warp product metrics to construct negatively curved metrics on M connect some sigma. Okay, so that will be the beginning of next time. I'll stop there.